Start. Welcome everybody to this event. It's a great pleasure for us to introduce the speaker of the 10th Majorana Lecture series. This series grew out of a joint effort of INFN Naples section and Department of Physics of Federico II University in June 2012. And along the years, we had distinguished lecturers, i.e. Riccardo Barbieri, Ubiraja Bancourt, Luciano Maiani, Nobel Prize winner Tuft, Franco Iachello, Gabriele Veneziano, Alessandra Buonanno, Christoph Wetterich, François Boucher, and today we are glad to welcome our 10th lecturer, Professor Josh Winn, from the Department of Astrophysical Sciences at Princeton University. It's appropriate to spend a few words about Professor Josh Winn. He's a physicist and astronomer at Princeton University. He earned a PhD in physics in the year 2001 at Massachusetts Institute of Technology, and later on obtained postdoctoral fellowships at the Harvard-Smithsonian Center for Astrophysics. He was on the MIT physics faculty for 10 years before moving to Princeton in the year 2016. His research goals are to explore the properties of planets around other stars, understanding how planets form and evolve, and make progress on the age-old question of whether there are other planets capable of supporting life. He was a participating scientist in the NASA Kepler mission and is a co-investigator in the Transiting Exoplanet Survey satellite mission. His recent work is focused on the orbital architecture of planetary systems. Let me just add that questions are welcome even during the lecture, and whereas the second opportunity for questions at the very end of the lecture, and this second session will be chaired by Professor Corona, who is among the audience. So now, please, Josh, you can begin your lecture. Thank you very much.
Thank you for that introduction. And thank you and the other organizers for this kind invitation. It's a great honor to be giving a lecture associated with such a brilliant physicist. And I also appreciate your forgiveness that I don't speak Italian. So this lecture will be in English. And let's begin. I'll share my screen. Okay. Now, so Gianpiero, are you looking at the correct slide or are you looking at the presenter screen? Are you seeing just the picture or are you also seeing other boxes?
It's the presenter screen. It's the presenter screen.
And how about now?
Perfect.
Good. Okay. So give me a moment. I just need to organize my screen so that I can also see the questions that might be coming up. And that will take a moment. Okay. One more thing. Okay, so I can view the participant list now while I'm speaking. And so as Gianpiero mentioned, I would welcome any questions that you have during the presentation. Please do feel free to interrupt me by using the raise hand feature to make sure that I don't say anything completely confusing, or if you just want to ask for more information about something that makes you curious. Okay, so I'm going to be talking about exoplanets. And most of the time, this is a field that is portrayed as a quest for another Earth, Earth 2.0, a place like we're seeing in this artist's depiction of a potentially habitable planet with water oceans on its surface and perhaps a giant moon in the sky. And that is definitely one of the field's most exciting questions that draws the most public interest. And I remain interested in that goal as a very long-term goal. But actually, most of what my group does, sort of here and now of this field, from my point of view, is not the Earth-like worlds, although we are making slow progress in that direction, but the very un-Earth-like worlds that we have discovered, for example, planets that might have oceans of magma and a star that is as large in the sky as 30 times the angular size of the sun. I like to study these strange new worlds as a way of simply exploring what the full range of possibilities is for planetary systems, to try to learn a thing or two about planet formation theory, and study some of the physical effects that may occur in other planetary systems that don't occur in our own. So what I want to share with you today is what is so strange about these new worlds? How do they violate the expectations of pre-exoplanet astronomers? And describe what we might conclude about the incompleteness of our theories for planet formation, as well as just introducing you to a few of my favorite new planets that I find especially interesting, and to describe some of the ongoing NASA missions that are discovering these new worlds. So first, let's remind ourselves what normal means in exoplanet science. You know, for centuries, our theories about planets and planet formation developed with only one example, the solar system. And early astronomers realized that the solar system has three striking patterns. First of all, the orbits of all the major planets are nearly circular, even though Newton and Kepler taught us that the general case is an elliptical orbit. Likewise, the orbits are all nearly aligned with one another. And this coplanarity is not required by the laws of physics. If you tilted the planetary orbits one way or the other, nothing especially bad would happen as long as the planets are spaced far enough apart. And so those two things pointed to some feature of the initial condition that might be needed to explain the circularity and coplanarity of the orbits. And then the third pattern was noticed only when observations became good enough to resolve these planets as actual worlds rather than as points of light in the sky. And it was then discovered that the planets seemed to be sorted by size and composition, with the small rocky planets, Mercury, Venus, Earth, and Mars, on the inside, and the larger, mostly gaseous planets, Jupiter, Saturn, Uranus, and Neptune, on the outside. So how did pre-exoplanet astronomers come to terms with these patterns? What was the prevailing theory of planet formation? Well, the story begins in a protoplanetary disk. These are the accretion disks of gas and a small percentage by mass of heavier elements that surround a young star after the gravitational collapse of the molecular cloud that gave birth to the star. The process is limited by the rate at which angular momentum can be transferred from the inner to the outer parts of the system. And so there's a prolonged period of several million years after the star has formed at the center when it is still surrounded by this accretion disk material called the protoplanetary disk. So the story is that planets form within this disk, and it's a rather complicated story. I'll just hit the highlights, and it has two main parts. So the first part is called planetesimal growth, and that refers to the fact that it's a bottom-up process. It does not begin with the collapse of large amounts of gas and dust directly from the disk, but rather builds up from the bottom, starting with dust grains, micron-sized bits of ice and silicates and metals that settle into a dense layer in the midplane of this disk over time, at which point the density becomes high enough that it becomes likely that they'll start colliding and interacting with one another, at which point they can gradually build up into larger objects if there is a preference for sticking rather than smashing each other to bits. And then eventually up to boulder-sized objects and even up to the size of a rocky planet. So this is where the rocky bodies of the solar system are supposed to have come from. Now I've drawn these arrows here, but of course we are very hazy on the details, especially the transition from pebbles and rocks up to boulder-sized. That depends on various aerodynamic effects. That's at a point where the gas drag on these solid bodies becomes important, and the aerodynamic effects can go either way. They can either cause the material to fall onto the star, or they can concentrate the material into clumps and vortices that allow further growth. And computer simulations of this process are still unclear on the details. But setting that aside, this is the first part of the two-part story of where planets come from. This is the origin of the rocky bodies. Then the next step attempts to explain where the gas giant planets come from. And there the idea is that there is a threshold at which point a planet begins to accrete gas. That if you are beyond a few astronomical units, that is a few times the Earth-Sun distance from the central star, that's cold enough for water to exist in its frozen form, and for other common molecules like methane and ammonia to also be solids. And so you have more material that can participate in planetesimal growth. And if a rocky planet happens to grow to about 10 times the Earth's mass, that's the threshold at which the surface gravity of the planet begins to overwhelm the escape velocity from the surface of the planet begins to overwhelm the thermal velocity of the particles of gas. And so the planet is able to begin efficiently accreting a lot of hydrogen and helium gas. And since there is so much more hydrogen and helium than solid material, the idea is that a planet that reaches this threshold will quickly swell up and become a gas giant planet. And so that part of the theory is called core nucleated accretion. The idea that you need a rocky core in order to nucleate the accretion of the surrounding hydrogen and helium gas. So this is a great story. It explains all three of the main patterns of the solar system. It explains the circularity and coplanarity of the orbits as a consequence of essentially the conservation of angular momentum and the existence of a flat accretion disk. And then it explains the compositional and size pattern through core nucleated accretion. The rocky planets can be anywhere, but gas giant planets have to be beyond a few astronomical units where there is enough frozen material to reach this threshold mass of 10 times the Earth's mass. In other words, a star system has a so-called snow line, beyond which there is enough snow to pack onto a growing protoplanet and promote it from a rocky planet into a gas giant planet. So it's a great story. Of course, it fits the data because it was invented to fit the data. And so the real test of a theory is its predictive power. And that's one of the other exciting reasons beyond the search for life to study exoplanet systems, to see if these three patterns will be universal. There's nothing in this theory that invokes any kind of special coincidences or unusual circumstances. And so if the theory is correct and if it's complete, then we should find that these patterns prevail everywhere. Now, even before the discovery of exoplanets, this theory gained some general credence because we started detecting the disks quite directly. I'll jump over the history of the discovery of protoplanetary disks. These days, we can just look to a spectacular telescope called ALMA, which is an interferometer operating at sub-millimeter wavelengths, which is especially good for these disks because it's sensitive to the thermal emission from the dust particles in the disk. And so you can map out where all the solid material is. And this is one of the more spectacular images that ALMA revealed around a star called HL Tauri, which was already known to be a young star for other reasons. And ALMA shows us the disk quite directly. It's a circular disk. We're just viewing it at an arbitrary angle, so it looks elliptical in profile. It's compared in scale to our solar system on the right side of this artist's depiction of the solar system. So it's a larger version of the disk that is thought to have existed around the sun. And what's really spectacular is you can even see dark lanes. So the orange and yellow, that's the emission from the dust. You also see these dark lanes, which are the absence of dust at the same level. And so it is tempting to think that we are seeing planets that are forming right now. The light entering our telescopes is revealing the process of planet formation as it happens, and that the planets, having grown from solid material, leave behind a ring of an absence of solid material. I should also say that interpretation is not unique. There are other instabilities, gas, dust instabilities in a disk that might produce these evacuated zones. But it remains possible that we are seeing the locations of forming planets. Unfortunately, the planets themselves are too small and too cold for ALMA to detect. So what we're seeing here are the tiny particles, but the planets themselves remain invisible. This is not unique. So ALMA has revealed lots of these protoplanetary disks around young stars with lots of different possible shapes, including some that have these wheel-like structures that I showed you a moment ago. Others have more spiral patterns. They sort of look like miniature galaxies, which is also attributed to some of the interesting fluid instabilities that can arise in these protoplanetary disks. So much better, though, would be to actually detect the planets and see what their orbits are like and what their compositions are like. The main problem, as I'm sure you're aware, with detecting planets is that planets are very small in comparison with the stars that they orbit. That's easily seen on this slide. What is not so easy to portray on a slide is that there is also an enormous contrast in the flux of light coming from the star and the planet. So the first thing you might think of doing if you want to find exoplanets is to take a telescope, take your best telescope with the finest possible angular resolution, point it at a nearby star, and look for the tiny little dots going around it and seeing what those planets look like. That turns out to be nearly, but not quite, impossible. And it's for the following simple reason. It's a contrast problem. So in this imaging method, the signal you're looking for is the flux of a planet relative to the flux of the star. That's what sets the required dynamic range of your image. And that's on the order of magnitude of the target area of the planet, which is, after all, only reflecting a small portion of the starlight, divided by the total surface area of a sphere that contains that planet's orbit, over which the light from the star is being distributed. So the planet can only reflect at maximum this fraction of the starlight, where A here is the radius of the planet's orbit. And if you run the numbers for, say, the Earth going around the sun, if you were trying to detect that from many light years away, it comes out to be 10 to minus 10. So you need to produce an image that is capable of revealing contrast with 1 part in 10 billion, which is totally impossible today. We do not have the technology to make an image with such good contrast, especially when the planet is projected so close on the sky to the star. So this is often compared in the popular press to the problem of trying to detect a firefly, which is buzzing around a few meters from a very powerful searchlight, and you have to do this from 1,000 kilometers away. Now, I've used this analogy very often in public talks. For this talk, I actually decided to check on the orders of magnitude to see if it works out, and it does. It checks out. That there is, one of the world's most powerful spotlights is in Las Vegas, unsurprisingly. It's about 10 million lumen. And if you look up the luminosity of fireflies, you get a wide range, but 10 to the minus 3 is typical. And so it really is a contrast on the order, within a few orders of magnitude of 10 to the minus 10. So it's a good analogy and it illustrates the challenge. So imaging has had some successes with very massive planets on very wide orbits, but most of our knowledge about exoplanets does not come through imaging at this point. It comes through more physically based techniques where we track some property of the star and use our knowledge of what's going on physically to deduce the existence of a planet. And so one of those techniques is the good old Doppler effect. We rely on the fact that the star itself is moving around the center of mass of the entire planetary system. And we can detect that motion through the Doppler shift that we observe, the time variable Doppler shift in the star's spectral absorption lines. It's very convenient that stars have these narrow absorption lines corresponding to atomic transitions in the outer atmosphere of the star, because that gives us this nice fiducial with which we can measure slight changes in the wavelengths of those lines over time. And so we will see the pattern of oscillations that allows us to deduce the existence of orbiting planets. Now, if you run the numbers again for this Doppler effect, we're measuring a fractional change in wavelength, delta lambda over lambda. And that can be of the order of magnitude of the orbital speed of the planet, which is the circumference of its orbit divided by the orbital period. And we have to divide that by the speed of light. And that comes out also So you can rearrange this using Kepler's third law to write it in terms of the period, only the period. That comes out to be, again, 10 to the minus 10, just by coincidence, for the parameters of the Earth going around the sun. So that doesn't sound any easier than direct imaging, but in fact it is. We are not at this point yet. We cannot do 10 to the minus 10. So we cannot detect the exact analog of an Earth-like planet going around a sun-like star using this method. But we're only about an order of magnitude away. Whereas in the case of imaging, we are many orders of magnitude away, maybe 4 orders of magnitude away. And so the Doppler effect has been very productive, not at finding Earth-like planets, but at detecting planets that are at least a little bit more massive or a little bit on shorter orbits, shorter period orbits, because the size of the effect increases for shorter period orbits, and they're just easier to measure because you can gather multiple cycles more readily. So the Doppler effect was the first technique that really started working in the mid-1990s and remains a very productive technique for learning about exoplanets. So one of the most famous Doppler planets that you may have heard of, if you pay attention at all to developments in astronomy, is around one of our nearest neighbor stars. So this is a view of the southern sky. We have the famous Southern Cross, constellation of Centaurus. And this is Alpha Centauri, which is often said to be the closest stars. It's a pair of stars, actually, to the sun. It's not quite right. There is a star that is literally a little bit closer. That's Proxima Centauri. It's a low luminosity red dwarf star that is part of the Alpha Centauri system. That is literally the closest star to the sun. And there is a planet going around the star. It was announced, I don't know, maybe 3 years ago. And it made front page news at the time. So this is a figure I'm taking from the New York Times, which shows that this planet, Proxima b, is not only a neighbor, but even more exciting, it's in the so-called habitable zone of that star. That is the range of orbital distances where the surface temperature on a rocky planet would allow for the presence of liquid water. And so since we think liquid water has been so important for life on the Earth, it really gets us interested when we find these planets in the so-called habitable zone for this quest for life. Now, if you did read about this in the press, as I expect many of you did, you might have seen it accompanied by an illustration like this one that shows the view from the surface of this new planet. With the star in the background, you can see that the mountains are covered with snow and there's some kind of mist rising up. There are some moons in the background. Of course, all of this is pure fantasy. We have no idea what the surface conditions might be like on this planet. Everything we know, every single bit of information is on this slide. All right, so this is the Doppler signal. This is how the planet was detected. We are measuring the so-called radial velocity, the velocity along the line of sight from us to the star over time, over 2 different observing seasons. In this case, that's what the 2 different colored dots are. And you can see there's a general tendency for the data points to go up and down, and they're roughly in agreement with the sinusoidal fit that is given by the gray line. So what we learn from the period of the best fitting sinusoid, we learn the orbital period of the planet. And from the amplitude of this sinusoid, we learn about the mass of the planet. The more mass of the planet, the more it's going to pull the star around. Actually, it's not quite as simple as that because we don't know the orientation of the orbit. So in fact, what we learn is the minimum possible mass of the planet. The planet could be more massive if the orbit is inclined relative to our line of sight, because only one component of the star's motion leads to a detectable Doppler shift. So we learn the period, and we learn the planet's minimum possible mass. It doesn't sound like much, but that kind of information is nevertheless what earned Michel Mayor and Didier Queloz half of the Nobel Prize in Physics, not this year, but the year before. They were the first ones to use this method successfully to detect what everybody agrees is an exoplanet around a sun-like star. So they didn't detect Proxima Centauri b. They detected this famous planet called 51 Pegasi b. So here is their data as well over the course of about a month. They saw the radial velocity march up and down in this very sinusoidal pattern. So the amplitude of the signal in their case was about 60 or 70 meters per second. And that along with the orbital period translates into a minimum possible mass of about on the order of Jupiter's mass. So this is presumably a gas giant planet similar to Jupiter. However, you probably noticed the time axis is in days. So Jupiter's orbit takes 12 years or so to go around the sun. This planet has an orbital period of several days. I think it's like 3 or 4 days. So it is much closer to its star than Jupiter is to the sun, much closer even than Mercury is to the sun. So if we go back to my little map of the solar system here, if the sun had a planet like 51 Pegasi b, we couldn't really put it on this slide. It's too close to the sun. We have to zoom in a bit so that we can see clearly the orbits of the inner planets. And this is where 51 Pegasi b would reside. Giant planet, very close to the star. And so sort of unimaginatively, we call these new planets hot Jupiters. And they make a mockery of the planet formation theory that I was describing earlier. The theory said that giant planets can only form beyond the so-called snow line, which is a few astronomical units, so would correspond to a period of a few years. Here we have a giant planet that is nearly as close to the star as it is possible to be and is heated to thousands of degrees Kelvin. And so clearly something was either wrong or incomplete with our theory for gas giant planet formation. Now, another interesting surprise of the early Doppler work were planets like this one, HD 80606, where we can see the Doppler shift of the star is quite variable in time and has a large amplitude, but is extremely far from being sinusoidal. It is very sharply peaked. So one day here, at around day 55, the star decided to start accelerating quite rapidly in the other direction before reversing its acceleration and coming towards us again. So what is this all about? This is because the planet's orbit is not even close to being circular. It is on a highly elliptical orbit with an orbital eccentricity exceeding 0.9. So that at one end of its orbit, it's out at 0.88 AU, which is a kind of Venus, Earth-like distance. But then once every 110 days, it comes screaming in to within just a few stellar radii of the star itself. And so it's a hot Jupiter on one end, and it's more of a terrestrial type climate on the other end. So this was a major surprise. It was surprise number 2. Another one of the patterns that we expected in the solar system was violated by the discovery of systems like this one with strongly eccentric orbits. And it's not unique. So here's going to be a chart of the orbital eccentricity, where 0 means a perfect circle, and as you increase it towards 1, it becomes more and more elongated. And a logarithmic axis of orbital distance on the horizontal axis, with some of our friends here from the solar system being marked. And here are the Doppler detected exoplanets. So the Doppler signal also reveals the orbital eccentricity in addition to the period and the minimum mass. And so here are those measurements. And these are mostly giant planets. Those are the ones that are easiest to detect. And we see their eccentricities are all over the place. There's a much broader range that we observe here than what we see in the solar system. And the one I showed you here up at 0.9, that is quite exceptional, but eccentricities exceeding Mercury's are quite common, at least for these giant planets that exist fairly close to their stars. So the real Jupiter is out here. Almost all of these planets are interior to the Jupiter, and they have a very broad range of eccentricities. So that too tells us that something was wrong or incomplete about our theories for planet formation. Now, I don't want to, this is not going to be a highly theoretical talk, but just to kind of, because I know you're curious, I want to describe some of the responses that theoreticians have had to these discoveries. The response has not been, let's throw out the entire theory of planet formation, it was completely wrong, and start from scratch. Not at all. Rather, the theorists have said, well, there's actually nothing wrong with the theory per se. It's just that we were not really paying attention to what might happen after the events take place in the standard theory. That is, there can be other chapters in the story that did not occur in the solar system, but that might occur quite commonly around stars elsewhere in the galaxy. For example, maybe stars in general form multiple giant planets with orbits that are too close to each other to be stable over the long term. And they have close encounters with one another, and that causes some randomization of their orbital elements and can, for example, cause one planet to be ejected and the other planet to lose a lot of angular momentum and take up a much more eccentric orbit around the same star. So maybe that is where the eccentric orbits come from. The hot Jupiters might come from the same process. It might come from a planet that gets scattered onto a highly elongated orbit, at which point tides between the star and the planet can gradually drain energy out of the orbit and cause it to shrink and circularize. But there are other theories for the formation of these hot Jupiters as well, and that remains a topic of vigorous debate and interest in this community. But for now, I want to return to the observational situation and describe our other main technique that is used these days for learning about exoplanets. And that one is conceptually even simpler than the Doppler effect. So what I'm showing now is a movie of the transit of Venus around the sun that took place last in 2012. That kind of thing happens around other stars too. That is, depending on the orientation of the star's orbit, the planets orbiting a star might be carried right in front of that star from our point of view. And even though we have no hope of actually seeing the silhouette of the planet moving across the face of the stellar disk, we can nevertheless detect it because the star appears to get slightly fainter in a periodic fashion. Every time the planet comes around, there's another one of these miniature eclipses. So this method is called the transit method. Similar to the transit of Venus, we say that the planet is transiting across the face of the star. And like I said, it's conceptually very simple. We are simply measuring a change in flux or a change in apparent brightness of the star. And the fractional change is the area of the planet's silhouette divided by the area of the disk of the star in the sky. So that's simply the square of the ratio of the radii of the two bodies. And here the news is much better than for the other techniques. If you were trying to detect an Earth-like planet going in front of a sun-like star, you need to measure brightness variations that are on the order of 10 to the minus 4. And that sounds a heck of a lot easier, and it is easier than these other methods which require 1 part in 10 to the 10. So this is a method that actually works. We do have, just barely, the capability today to detect Earth-sized planets going in front of sun-like stars. And we have a collection of many of these objects. So it's the only method so far that has worked in that sense to get us as far as detecting Earth-sized planets. Furthermore, the transit method is the one I love the most, and not only is it responsible for 3/4 of all known exoplanets today. So we know of about 4,000 exoplanets. Transiting planets represent about 3/4 of the total. But it also enables all kinds of other really fascinating follow-up observations to learn more than just the size of the planet, the mass of the planet, and its orbital period. We can learn more than we have any right to know about some of these planets using tricks that rely on transits. Let me give you some examples. One is that we can learn a thing or two about the contents of the outer atmosphere of the planet. And that comes by doing transit spectroscopy. So for example, one of the most optically active species in the outer atmosphere of a hot body, like a hot Jupiter, is neutral sodium and the famous D lines that arise, this fine structure splitting that you see in the optical of a sodium atom. And so if you observe one of these transits at an arbitrary wavelength, say 600 nanometers, the planet will block a certain fraction of starlight. But if you observe the transit within a filter that is centered on that 589 nanometer wavelength of the sodium doublet, now, and if there is sodium in the outer atmosphere of the planet, suddenly the atmosphere is more opaque than it was before because of the strong absorption by sodium, and the planet looks a little bigger. It blocks a larger fraction of the starlight. So that's transit spectroscopy. So the game is to perform these measurements not at one wavelength, but over many wavelengths. That is to do spectroscopy throughout a transit and see if the apparent size of the planet changes with wavelength in a way that agrees with a model for the absorption by atoms or molecules or ions, whatever you think might be in the atmosphere. And that has actually worked. So this is real data. that revealed neutral sodium in the atmosphere, the outer atmosphere of one of the hot Jupiter planets. And through other painstaking measurements like this, molecules such as carbon monoxide and water vapor and methane and ammonia have also been detected, at least tentatively, in the atmospheres of many transiting giant planets. This method requires very high, large telescopes and very precise observations. So we can't quite do this yet for truly Earth-like planets, but we can start to do it for planets more on the size of Neptune and Uranus, and are gradually working towards the ability to study the atmospheres of terrestrial type exoplanets. And perhaps with the James Webb Space Telescope, which is the NASA mission and ESA mission that's due to be launched, I think it's in October of this year, perhaps the frontier will be pushed down to smaller planets using this technique. So that's one very exciting aspect of this field, is studying the atmospheres of these planets. Another one that I happen to specialize in my group is more related to orbital dynamics and geometry. And that is, well, the background here is that if you look at the sun is rotating with a rotation period of about a month. And the sun's rotation axis is nearly, but not quite, perpendicular to the Earth's orbital plane. That is, the sun has an obliquity of about 7 degrees. And using our current technology, we can actually measure the obliquity of stars with exoplanets. You know, the planet formation theory would predict that the obliquities should be quite low, because the star and the planets both inherited their angular momentum from the same source, from the original random angular momentum of the cloud that underwent this gravitational collapse. So how can we possibly measure this? We can't resolve the star. We just see it as a point of light. We cannot resolve the orbit either. So how can we tell which way the star is rotating? Well, it's really wonderful. What we do is we fuse together the Doppler technique and the transit technique. So like we know now, we detect these transits by monitoring the brightness of a star throughout one of these events to see it go down. If we could view the same event through one of our Doppler spectrographs that are capable of these very precise wavelength shifts, if we could somehow put our eyepiece on one of those instruments, we would see that the star looks strange. Half of the star is blue and half of it is red relative to the average, and that's because the star is rotating. Half of the star is rotating towards us and is blue shifted. The other half is rotating away from us and is red shifted. And usually there's a perfect cancellation of these two effects, and so the total integrated light that we capture with our telescopes has no net Doppler shift due to rotation. During a transit, the symmetry is broken. And if the planet is blocking some of the blue light, then our spectrograph observes a net redshift. And then that vanishes when the planet crosses the symmetry axis and becomes an anomalous blue shift on the other side. So that's the signal we would see if the star has a low obliquity and if it's just like the solar system. Whereas if we tilt the star, so now it has an obliquity of say 60 degrees, now the planet is only crossing the red side of the star during its transit, and the anomalous Doppler shift will be a pure blue shift. So that's the game. You monitor the Doppler shift of the star, not over the whole orbit, but just during the transit. And the size and shape of this effect will tell you the rotation rate and the obliquity of the star. So this is an effect called the Rossiter-McLaughlin effect, after the two people who came up with this idea in the 1920s during the study of binary stars rather than planets. Applied to planets, though, it's been very interesting. We have lots of cases now, this is real data for a certain hot Jupiter, where the anomalous, you see an anomalous redshift, that's a positive excursion followed by a negative excursion, and that represents a well-aligned prograde orbit with a low obliquity, like the solar system. We also have a lot of cases where we see either a pure blue shift or a pure red shift. So the planet is apparently going over the north and south poles of the star. And the most wonderful of all, we have a small but interesting collection of objects where we see the inverse of the pattern that I showed you previously. It goes negative than positive, that means the planet is on a retrograde orbit relative to the star. The star is rotating one way, and the planet is revolving in the backwards direction. So that too tells us that something is missing from our standard theory of planet formation. And this again points to possible dynamical interactions between planets that cause them to some degree, randomize their orbits over time. Although even simulations of that effect do not often lead to polar and retrograde orbits. So I think there's bound to be another category of explanations as well that may require us to tilt the entire disk away from the star during the first few million years after its formation. And the mechanism for doing that kind of thing is still really up in the air. Another thing I like to study are the tidal interactions. So one nice thing about these close-in giant planets is that they interact much more strongly with the star than any of the planets do in our solar system. And that allows us to view the consequences of, in this case, tidal spin-orbit interactions in a way that we would have difficulty doing in the solar system. So these are good old-fashioned gravitational tides. The planet, for example, raises a tidal bulge or tidal oscillations on the central star. And so because of the loss of symmetry associated with those tidal bulges and oscillations, the planet and the star can now exchange angular momentum with one another. And furthermore, the friction, the viscosity associated with the flows on the stellar side lead to a dissipation of energy. So there are instantaneous exchanges of angular momentum and then a long-term drainage of energy from the system. And there's a wonderful theorem you can prove just from these simple considerations of energy and angular momentum. It was worked out in the 70s and 80s, that if the system exceeds a certain total angular momentum, that is orbital plus rotational angular momentum, exceeds some critical value that can be written down in terms of the masses of the bodies and the moments of inertia and the gravitational constant, then the planet, under the dissipation, the system evolves into spin-orbit synchrony. This is what's happening with the Earth and the Moon, for example. The Moon's orbit is widening, the Earth's rotation is slowing down, and they are approaching, over billions of years, this eventual state of spin-orbit synchrony. However, most of the hot Jupiters do not have enough orbital angular momentum for them as a whole to exceed this critical value. So what you expect instead in that case is that the planet surrenders all of its orbital angular momentum to the star, spinning up the star, but during that process, the orbit is shrinking and shrinking until the planet becomes engulfed. There is no stable final solution. It ends with the merger of the star and the planet. And that would be really interesting if it exists, if that does happen. It would tell us something about the lifetimes of these hot Jupiters and therefore a clue about their formation history. And it's also just interesting physics. The considerations of energy and angular momentum tell us that this is the outcome, but they do not tell us how long it should take to happen. That depends on the so-called Q factor of the star, which is it's the tidal quality factor, like from the simple damped harmonic oscillator. That is, when you start the star oscillating, how long does it take for that energy to be dissipated through viscosity or other processes? And stellar astrophysicists would like to know. That's one of the main uncertainties in this whole business, because it's very hard to calculate from first principles. And so if we could detect it by studying hot Jupiters, we could detect this orbital decay, it would be an important input in their theories of stellar structure and evolution. So we can do that with transiting planets because it's now been, in some cases, 5, 10, even 15 years since the discovery of these planets, and we can time the transits very precisely to within minutes. And so this, for example, is for a particular hot Jupiter. What I'm plotting here is the so-called timing deviation, that is, the departure from periodicity over as a function of the orbit number. So we can track these coherently and maintain knowledge of the orbit numbers as an integer. So if the orbit were strictly periodic, the timing deviations would be consistent with 0, as they are in this case. So this is the case of a hot Jupiter that does not show any evidence for orbital decay. However, very recently, we have found one case where we're pretty sure that's what's going on. This is the WASP-12 system. It's one of the closest of the close-in orbiting hot Jupiters with an orbital period of about a day. And it does show deviations that show negative curvature. That's an indication of a negative period derivative. So the orbital period is shrinking, and we think we can attribute that to this tidal orbital decay. So it tells us the dissipation factor for this star happens to be on the order of a few times 10 to the 5. And it also tells us that the lifetime, at least of this hot Jupiter, is only a few million years. So that's very short by the standards of stellar astrophysics. These stars last for 10 billion years. So we seem to have caught this particular hot Jupiter just a moment before it's going to be destroyed, which is also interesting. So I've been going on now for a while. And by the way, I haven't noticed any questions. I hope that doesn't mean I've been oblivious. So please do feel free, again, to interrupt me with any questions. But what I want to turn to next, if there aren't any questions, is the heartbreaking thing about the transit method. But the transit method is wonderful, as I've described it, but it does have this one serious problem, which is that most exoplanets do not transit. If we have a star here, and there's a planet going around it, who gets to see transits? Where on this slide are the observers that get to see transits? Well, if the orbital distance is A, for example, it's only observers that are inside this cone here in 3 dimensions that would be able to look towards the star and see the planet in front of it. So what is the likelihood that you're going to be in this cone? Well, the planet does go around, and so it sweeps this cone around into a band on the celestial sphere surrounding this star, and that band has a width of the diameter of the star divided by the orbital distance. That's the angular width of this shadow band. And so you can work out the transit probability. The area of the shadow band divided by the total area of the celestial sphere goes as the radius of the star divided by the orbital distance. And so for the Earth going around the sun, that's 1 part in 215. What that means is that for every planet we see with an orbital period of a year or an orbital distance of 1 AU, for every transit we detect of a planet like that, we know statistically there are 214 of them out there that look just the same, but that don't transit. Their orbits are just not lined up. We are not viewing them from the right angle. So in that sense, this method is great when it works, but it's extremely inefficient. It misses most planets. Just to illustrate how brutal this selection effect is, let's say we're looking, question, please, from Gaetano Fiore.
Yes, excuse me, it was an old question. How do you know that Pegasi 51 is a gas planet and not a different one? I missed that.
Yeah, I didn't explain it, so it's a great question. So the Doppler method reveals the minimum mass. And that comes out, I think in that case, to be about half the mass of Jupiter, which qualifies as a giant planet. But we don't know for sure in a case like that if all we have is the minimum mass. For the transiting planets, we not only know the minimum, we know the true mass using the combination of the Doppler method and the transit method. The transit method tells us that the orbit is viewed exactly edge-on, so there's no more ambiguity in the orbital orientation. And that means the Doppler method does tell us the true mass, not the minimum mass. Furthermore, the transit method tells us the diameter, or so we can calculate the density of the planet, and it comes out to be a gram per cubic centimeter, half a gram per cubic centimeter. That's the density of the gas giant planets.
Yeah.
So that's the main evidence, is the density for the cases where we have both the size and the mass. But strictly speaking, for the Doppler-only planets, there is an ambiguity.
Okay, thank you very much.
Sure. So on this slide, I'm going to illustrate this terrible selection effect. So it's a log-log scale. We have the planet size relative to the Earth here, and the planet orbital period in days. And let's just pretend the universe is full of planets that exist with properties uniform in this plane. So all the gray dots here are the planets in our neighborhood of the galaxy. Let's say you observed all of these stars for 4 years straight with a 1 meter optical telescope that is limited only by the theoretical shot noise, the Poisson noise from the photon nature of light. So kind of idealized transit survey. Which ones would you detect? you'd only detect these ones that I've colored blue here. This is not at all a representative sample. This is a strongly biased sample. The reason that it fades off as you go to the right is because of the low transit probability for distant orbits. There's also a diagonal line here below which you can't detect it even if it is transiting because you lack sufficient signal-to-noise ratio. That is, you don't collect enough photons. And then there is a horizontal line here beyond which you lose a lot of sensitivity simply because you're only observing for 4 years and you want to catch at least a few events to be sure that it really is an eclipse and not just some kind of fluctuation. So it's a very, very biased view that we get from our transit surveys. And that will help to explain what I'm now going to show, which is the history and development of this field of transiting exoplanets. So the same axes, but now I'm going to show you real data. And I've used stars to represent the planets in the solar system. But as of 2005, we only had 7 of these transiting exoplanets. And they were all up here in the upper left part of the diagram, with orbital periods of a few days and sizes comparable to the sizes of Jupiter and Saturn. That is, these are the hot Jupiters. Those were the entire story of transiting planets as recently as 2005. 2008, we hadn't made a tremendous amount of progress. There was a space mission launched by a consortium of European, I think including Italy, called Corot, that detected one of the first smaller transiting planets using a space-based and much more sensitive instrument. But still, we were mostly looking at hot Jupiters. By 2011, we started getting the results from a major NASA mission called Kepler, which kind of opened our eyes to some of the smaller planets that had been missed before. And 2014, that mission really got going. And here's where we are now. So the Kepler mission is over and is responsible for having detected most of these planets. And what Kepler taught us is that all these hot Jupiters, they're a lot of fun, they're very, very interesting, but they are intrinsically quite rare. Only about 1 out of 200 stars like the Sun have a hot Jupiter, let alone a transiting hot Jupiter, which is down by another order of magnitude. Whereas it's more like half, or maybe comparable, it's order unity stars have these kinds of planets, planets that are more kind of in between the size of the terrestrial planets and the Uranus and Neptune planets, but that have orbital periods shorter than the corresponding planets within the solar system. So these planets go by several names. Some people call them super Earths, some people call them sub-Neptunes, but those are the current frontier, is trying to understand. So those are quite common. So any theory of planet formation has to explain these planets. They cannot be written off as exceptional cases. And that's part of what makes them interesting. Let me go into just a little more about this Kepler mission, which was so revolutionary for our understanding of exoplanets, that detected the majority of the known exoplanets today. It was a NASA mission that used a 1 meter diameter optical telescope in space. It actually did not orbit the Earth. It has its own orbit around the Sun. And that's for, you want to be away from the Earth because scattered light from the Earth and other effects relating to low Earth orbit really prevent you from doing precise photometry very well. So Kepler was sent in its own orbit around the Sun. It had a relatively wide field of view, about 10 degrees on a side. That's illustrated here. For those of you who do some stargazing, this is the summer triangle, Vega, Deneb, and here's Altair. This is where Kepler looked for 4 years straight, looking at several 100,000 stars. It was designed specifically to be capable of measuring the frequency of occurrence of Earth-like planets with Earth-like orbits around Sun-like stars. It actually didn't quite do that. It came awfully close, but it turns out that the noise levels in the flux measurements were just a bit too high to give a really accurate answer to this question. So that by that very, very strict engineering kind of standard, the Kepler mission failed. But nevertheless, everybody considers the Kepler mission an enormous success because it discovered thousands of other planets that turned out to be very, very interesting and informative. So this will show you why we need to do this from space. This is the same transit or the same planet rather, transiting the same star, as viewed with a 1.2 meter telescope on the ground, and as viewed by Kepler. So we were looking at relative brightness against time, and take note of the y-axis here. We're looking at rather small brightness variations. And here with the ground-based telescope, you can certainly tell that a transit has taken place, but there's a lot of noise in the measurements, and that's due to the Earth's own atmosphere, mostly, that corrupts our brightness measurements by focusing and defocusing starlight in a color-dependent way. That really messes around with our ability to perform great photometry. Furthermore, the reason this observation got interrupted is because the sun came up. Whereas that, you can arrange for that not to happen in space with the right orbit. And so those two advantages are what make the Kepler telescope and other space-based instruments like Corot and a new mission. That's what makes it possible to really detect small planets. You can also see here that this little fluctuation here, that is a real thing. That's not an instrumental effect. You would never have seen it with the ground-based telescope. What's happening there is that the star, like the sun, has dark spots on its surface. And it just so happens that the planet crossed over one of those dark spots during the transit. And so for a moment, it was blocking a relatively low luminosity part of the star. And so the loss of light was reduced, and that produces a little glitch in this so-called light curve. So you can see all kinds of wonderful details with the quality of space-based photometry. One of Kepler's main accomplishments, I think, is this diagram. This is now a histogram. This is showing the histogram of planet sizes measured in Earth radii. So this is the average number of planets per star as a function of the size of the planet. And what you see is there is a bimodal distribution. First of all, you see that the giant planets, they exist, but they're quite rare. By the way, this is after an attempt to debias the survey, to remove those strong selection effects, which is itself a difficult problem. But assuming that was done correctly here, you see that the giant planets are quite rare. These smaller planets are much more common. And there seem to be two kinds. There are planets that are just a little bit bigger than the Earth, and then there are planets that are around 2 or 3 times the size of the Earth with a deficit in between. Now, the wonderful thing about this, the reason why I think it's one of the most important accomplishments, is that this is a very rare case in exoplanet science where something had been predicted in advance of being observed. This had been predicted by some theoreticians as a consequence of the strong irradiation of the planet's atmospheres by the star. So these are all short period, close orbiting planets. The interpretation here is that these bodies are rocky planets, but they are ensheathed with a relatively high amount of hydrogen and helium, about 5% or so by mass. So not nearly gas giant planets, but still have a sheath of hydrogen and helium gas. And even a small fraction of gas by mass will expand because of its large scale height to increase the size of the planet quite a bit. Whereas these planets down here are bare rocks. The hydrogen and helium has escaped because of the heating of the planet's surface and the subsequent increase in the thermal velocity of these gas molecules. In fact, you can drive a hydrodynamic wind off of the planet by heating the surface. So these theorists had predicted this effect, and in particular, they predicted that it would be a sort of threshold phenomenon, which is not easy to explain succinctly, but they had predicted why there would be a bimodal distribution as opposed to a continuum, and in fact, that has been observed. Now, I don't know, this interpretation is not necessarily unique, but I'm impressed with this kind of a prediction being confirmed. Another result I find especially meaningful is the discovery of systems like this one. So again, we're looking at brightness, and we're looking at very small changes in brightness over time, in this case, over about 450 days. And at first glance, it just looks like random noise, and it is. The fluctuations that I'm pointing at here, that's just photon noise fluctuations and the imperfections in the instrument. But you also see these little spikes going down to like 0.9985 or so. Those are real, and that is a transiting planet. In fact, what makes it look so confusing, it doesn't look periodic at all, is that there are at least 6 planets going around this star, each of which is transiting. So we were seeing the superposition of 6 different sequences of planetary transits. This system is called Kepler-11, and what makes this remarkable is not only is it very, very flat, this planetary system, in order for all the planets to be transiting, but they're all very close to the star. They're all packed in to what would be Venus's orbit around that same star. In fact, 5 out of them are interior to what would be Mercury's orbit around that star. So that is remarkable. Like I said, there are a lot of these close orbiting planets, but what I find kind of profound is that these are not rare. Kepler found enough of these that we can conclude that somewhere between a third and a half of Sun-like stars have these miniature versions of planetary systems. So there must be some kind of a switch that gets thrown at some point in the planet formation process that can either lead to these miniature planetary systems or the more spread out systems like the one that we live in. And we don't know what that switch is, what factors contribute to the formation of these types of planets as opposed to what we used to think were normal planets. Okay, I see we have a question from Android Blue Droid.
Yeah, I'm sorry. I'm taking the class from my phone.
Sure.
So the question was, first of all, how would you explain the fact that in this multiple system, usually the entire set of planets look like they have the same dimension, and there are not any hot Jupiters or in general any Jupiter-like planets in the system, and whether it's possible or not that there are other gas giants in the system that are actually maybe have too high an inclination for us to see them, or maybe it's just a period problem.
Yes, fabulous question. So to answer the second part, there are definitely planets around these same stars that we are blind to. Because even if the orbits are tilted by just a few degrees, that would be enough to prevent them from transiting all at once. So there are undoubtedly other planets and more distant orbits that we are not seeing. In fact, there are stars that have these compact systems that we have also been following with the Doppler method. And we can see there's an outer giant planet in addition to the inner system. In fact, I think it's something like a third of these compact multi-planet systems do have a wide orbiting outer giant planet. Now, your other question was about the correlations between the planet sizes. And I think that's especially, it's wonderful to detect a planet, but more informative, I think, are going to be the correlations between different planet properties in the same system. And they are correlated. So one of my colleagues, Lauren Weiss, discovered that the sizes are quite strongly correlated, as are the orbital periods. The orbital periods tend to be uniform in the logarithm of the period, so they're evenly spaced in log period, and the sizes are much more alike than you would get if you just picked planets randomly from different stars. So that surely, it's telling us something about that planet formation is a somewhat deterministic process, that in the same conditions you form the same kinds of planets with regular spacing. So at least that gives us hope that there can be a predictive theory of planet formation. But I think it's fair to say that none of the theories, certainly none in advance, made a specific prediction in this regard, or are even especially promising in this regard. That might be a little unfair to our theorists at the moment. But I don't know of a great theory that makes this seem like a natural outcome. Okay. I see that I'm already in overtime, which is a shame because I have so much more I want to share, but I want to respect everybody's time. And so I think I will just pick a few of my favorite systems to really focus on, these kind of weird one-off systems. Okay, here's a nice one. So this one's called Kepler-78. Again, we have brightness variation against time. This time it's centered on 0 rather than 1, so we're measuring the drop in brightness. The star dropped in brightness by a little over 200 parts per million. That means that corresponds to a planet of I think it's 1.4 times the size of the Earth, so a small planet. But look at the time axis. This planet makes a complete cycle every 8.5 hours, rather, not days. So this was kind of a surprise that the hot Jupiters, they can have periods down to about a day, but the smaller bodies, they can have periods down, I think the record holder is about 4.5 hours This is one of the shortest period ones we're looking at now at 8.5 hours. So that's really close. That's almost as close as it is physically possible to be without the planet getting destroyed. What's also wonderful, you've probably noticed if you're used to looking at data anyways, that there's another dip here in between the transits. What's that all about? That's a wonderful thing. So we have to imagine here that the planet is going in front of the star, and when it's in front, that's when we see the transits. But then as the orbit continues, the planet's strongly illuminated hot day side, the side facing the star, comes into view. And so there's a gradual rise in the total light that we are receiving because there's a contribution from the planet. But then as it continues further, there comes a point when the planet goes behind the star and we lose that light. And that's when we see this dip here in between the eclipses. So that's great because we can measure the planet's own reflectivity, or in this case, partially its own thermal emission from the amount, if we do this at infrared wavelengths, we can measure the planet's own thermal emission. In other words, we can measure the planet's temperature on the day side, which of course confirms that these planets are heated to thousands of degrees. And that is the inspiration for our space artist friends to come up with pictures like this one. This probably is a rocky planet, and the temperature is well above the melting point of all of the common rock-forming minerals that we have. And so this likely is a planet where there are magma oceans covering at least the side of the planet facing the star. So that's a really fun one. Let's see, what else do I want to show? Oh gosh, okay, I have to show you this one. So this is a planet system called Kepler-16. Again, we're looking at brightness against time, but here we're seeing I've colored the different kinds of brightness dips with different colors. There are these blue dips that go down to about 0.87. That's way too big to be a planet. Then you have these more planet scale dips here, but they're not periodic, and there seem to be different kinds of them. There are the brown ones, the green ones that differ in detail, and the red ones, which you can't even really see on this scale. What is going on? Why are there 4 different kinds of eclipses? The reason is that this is a pair of stars, a yellow star and a red star, and they are in a binary orbit, and we are viewing it from the side. So we see the yellow star eclipse the red star, we see the red star eclipse the yellow star. And in addition, there is a planet, hopefully you can see me tracing it out on the slide, whose orbit surrounds both of the stars. Every time it comes around, we see it go across the yellow star and then the red star, or vice versa. And everything fits. You can fit a 3-body model to this brightness data, and you can get all the timings and durations of the eclipses just right. So there's no doubt that this is a case of a so-called circumbinary planet, which is interesting in itself, that planets, that there are disks that surround 2 stars, and that planets can form within those disks. Of course, it's also interesting to those of us who grew up on science fiction to know with certainty that there are planets that have 2 suns in the sky. So just in the minute that remains, I feel I should bring you to the frontier. I've been talking about a lot of the discoveries that have been made with ground-based instruments and with the Kepler mission. But we have gone beyond the Kepler mission at this point. The Kepler mission ended a few years ago, and it left behind a wonderful legacy. But during the main part of its mission, for that continuous 4-year observation, it was pointed in a certain direction in the galaxy, and so it gave us thousands of planets that happen to exist within this cone of the Milky Way, but left us relatively ignorant of the same kinds of planets that must surely exist closer to the sun, that didn't happen to be in that direction in our sky. So that is the main purpose of NASA's ongoing mission to detect transiting planets. It's called the Transiting Exoplanet Survey Satellite. It uses 4 relatively small wide field cameras. Let me show you what those cameras look like. They look like this. They are very modest. They are 10.5 centimeters in diameter, so 10 times smaller than the Kepler mission, but that's what we wanted to do. There's always a trade-off between the diameter of the telescope or the lens and the field of view. And we want a very wide field of view to examine all the bright nearby stars that are all over the sky. So TESS is ongoing now. The way it works is that We can't observe the whole sky at once. I wish we could do that. Instead, we use these 4 cameras, and they're all pointed in different directions so that at any one moment, we have a tall rectangle on the sky that we are monitoring. And we look at it for a month, and then we move on. We reorient the spacecraft to do another so-called sector. And so over the course of a year, we cover one hemisphere of the sky. And then in year 2, which just ended quite a few months ago, we covered the other hemisphere of the sky. Now we're in our year 3 when we are beginning to repeat the sky survey in order to build up a longer database of time coverage. So there are a lot of wonderful things about TESS that I won't have time to share with you, regrettably. But one thing I want to emphasize is there is a lot of data. So each of these 4 cameras has 4 CCDs, each of which has 4,000 pixels in each direction. So there's a ton of data. This is a close-up of one of those camera fields showing the large Magellanic Cloud, as well as all of the stars that can now be searched for eclipses, as well as any other type of brightness variability. So the TESS data have been useful to a very wide community of astronomers who are interested in really anything that can be profitably studied with a 10-centimeter telescope. TESS will give you beautiful data. And what I think is most important of all is that all the data are publicly available. This was an important part of the design of the mission and has proven to be very successful in having an enormous, immediate scientific impact of the mission. So rather than talking about all the wonderful TESS discoveries, which I'd be happy to do if we have time in our questions, I'll just end on this note, that NASA, I think correctly, sees TESS as an important bridge between the Kepler and other missions that came before, which taught us a lot about exoplanets, and the next generation telescope I mentioned earlier, the James Webb Space Telescope, which will be very good at doing things like transit spectroscopy and studying the atmospheres of transiting planets. But it would be very strange to use this giant multi-billion-dollar telescope to study a distant faint star from Kepler, when we know statistically that it's very likely there is a much brighter, maybe 100 times brighter star right in our neighborhood where we get much better quality data. And that's what TESS is about, in part, is to find the best, brightest targets that will be studied with James Webb. And that's one of the things that we can all look forward to in the years to come, is following up on these discoveries to learn ever more fine details about these planetary systems. Okay, well, thank you for indulging me in what I know has turned out to be longer than an hour. And I am happy to stick around and answer any questions that you might have about the presentation. So I will stop sharing my screen, although I'll be happy to go back to a slide if it's relevant to a question. So let's see, I see Maurizio Paolillo has a question.
I was wondering, I know that the current status of the solar system is believed to be due in part to the migration of planets at some stage of its evolution. So I was wondering if there is evidence that this migration happened in other solar systems.
Yes, so the migration you're probably referring to is a gravitational interaction that can take place between a massive planet and the protoplanetary disk, which might have, say, a tenth of the mass of the star itself. So it's kind of a massive flat disk. And if there's a Jupiter mass planet that ends up growing within it, then the gravity and the motion of the planet will cause spiral density waves to propagate through the disk through gravitational interactions. And then the density contrasts in the disk can act back on the planet to change its orbit. And that calculation was actually done in the 1980s in the context of the satellites of Jupiter and Saturn, not exoplanets. And it was never really clear why that calculation wouldn't apply to the solar system. But the evidence that it probably does actually comes entirely from exoplanets, at least at first. And that's the hot Jupiters and the other close-in planets that are supposed to have formed farther out. How did they get where they are? I had been emphasizing the dynamical explanations involving planet-planet interactions, but it could also, in fact, maybe even as likely to be due to these planet migration processes that occur between the planets and the protoplanetary disk. So there's a large community of people that are simulating that process, trying to see how fast it is, trying to see how to get it to stop, and see if you can match the observed properties of the exoplanets that way. Let's see, another question from Gaetano Fiore.
Yes. Is it possible to use the Doppler method when to distinguish more planets? I mean, with the same star. I guess that this might be possible if they have very different periods.
Exactly.
So that,
yeah. So what you measure with the star is the summation of all of the various motions due to different planets.
Yes.
So you have different Fourier modes basically in your signal. Yes. And if you have a long enough time baseline and good enough coverage, you can tell that there are multiple planets, and you can measure the mass and orbital properties independently. However, for these multiple planet systems where you have 5 or 6 planets, you need a lot of data to be able to pick them all apart. So there's usually a period of confusion when you don't even know how many planets. You know there are planets there, but you don't know how many or what their orbital periods are.
Yeah, I see. Thank you.
Let's see, Mario Nicodemi.
Hi, Josh. Thank you. That was really an amazing talk. I'm in a totally different field, and so I'm asking a naive question because I was really fascinated by the amount of fantastic data and complex data that you have. I'm also overwhelmed by that. In the sense, I didn't realize whether we start having in your field, say, guidelines or principled ideas whereby we can make sense of such a variety of complicated and diverse cases. So I don't know if you can add something.
Are you referring to the data-oriented aspects of the field, like classification and?
Yeah, interpretation of the variety of behaviors that you see.
Yeah, if you're referring to the theory of why the exoplanets are the way they are, that's something I didn't emphasize so much. I explained the standard theory and some additional chapters that might be added on to the end, but that is a very active area of research, and it can be done at lots of different levels. Planet formation, it's a wonderful physics problem, but it is not a particle physics problem. It's extremely complicated and messy. It's what a theoretical physicist might call an extreme case of phenomenology, where there are processes happening on the level of micron-sized dust particles, and then there are large-scale instabilities of this huge gravitationally supported disk. So it's a very complex problem. Some people pursue it analytically. Some people pursue it with giant numerical simulations. Most of the I think burning questions are about these close-in planets and the eccentric orbits. How to present picture how to determine what determines whether a planetary system will evolve in one direction towards a more chaotic orbital elements and in one direction towards a more quiescent and long-term stable configuration. What are the processes that modify planet orbits? I've already talked about the tidal effects that might be strong for some of these and might end up sculpting some of the planetary properties as well. So there are a lot of theoretical problems that have been spawned by the discoveries of exoplanets. And then there's a whole other branch of theory, a very active subfield that studies these planets from a more traditional planetary science point of view. What is in their atmospheres? What are the possibilities for their surfaces and for their interiors? At the moment, I feel badly for those people because we don't have that much data. It's very fragmentary, our knowledge of the atmospheres and interiors. But it's something that's likely to grow in the years to come as our data becomes better and better. So that was kind of a vague answer to your question, but I'm not sure I can do much better at this point. Let's see, Luigi Mancini, whose name is familiar. Are you the one who also works in exoplanets?
Yes, indeed. We meet already in Porto several years ago. Well, yeah, great talk, by the way. Thank you. I have a question about the orbital obliquity angle of hot Jupiter.
Good.
You know that there is a theory about that the orbital obliquity of hot Jupiter is correlated with the temperature of the parent star.
That's right.
But there are many exceptions. So I would like to know what is your feeling now about
Yeah. So that's kind of a second order question. So the data I provided just showed that there is a range of obliquities. What Luigi is referring to is that there's a pattern within that. That if you look at stars that are somewhat more massive than the sun, those are the ones that have the widest range of obliquities and backwards rotation and so forth. Whereas if you look at sun-like stars and less massive stars, those are almost, at least for the hot Jupiters, those will have very low obliquities, similar to the sun. So I'm not sure what's going on there. I suspect that what happens is that these hot Jupiters form through a process that often randomizes their orbital orientations. Or, there's actually increasing evidence that the entire protoplanetary disk can get tilted due to the action of some wide orbiting, say, companion star or a wide orbiting distant planet that got thrown out onto an inclined orbit. So if the whole disk, for example, starts to precess under the gravitational influence of a distant star, then all the planets form on orbits that are misaligned relative to the star. And the reason we don't see that for the hot Jupiters around the low mass stars is because tidal effects can, in addition to synchronizing and circularizing the orbit, they also tend to align the orbit and the spin. So I think that's what's going on, and there's some circumstantial evidence for that. For example, the only exceptions we see to that pattern is that the low mass stars have low obliquities are the giant planets that are in wider orbits. Those do have a wide range of obliquities as well. And that we would expect if tides are the solution, because if the orbit is wide, tides are not as strong, and the planet did not have the ability to reorient the star. So if I had to guess today, that's what I think is going on.
Okay, thank you.
Sure. Giovanni.
Yeah, I have a question related to the unity normality of our solar system. So as you said, first of all, thank you for your seminar. It was very clear and very stimulating, very much stimulating. Thanks a lot. So we started from having only our solar system. So we thought that what we observe is normal. And then we are in a situation that seems that our solar system is unique. So I don't want to go on the other side, but it seems really that the complex and chaotic mechanism involved in planetary system formation makes our solar system like ours, and like planets like Earth, very, very rare. So
yeah, that is often said, and and popular articles as well emphasize that point, that solar system might be the exceptional case. I'm not willing to say that yet. I don't think we know. Certainly we know that if you pick a sun-like star, there's maybe a 1/3 or 1/2 chance that it has detectable planets that do not resemble the solar system, these compact multiple planet systems or hot Jupiters. But that leaves the other 2/3 or 1/2 of the stars that might have more solar system-like configurations. We just can't detect them yet. We have great difficulty detecting the true analogs of any of the planets in our solar system if we were far away. Mercury, Venus, the Earth, they're a little too small to be readily detectable. And the giant planets produce big signals, but they're over much longer timescales, tens, 100 years. And so we have much greater difficulty detecting them. So I don't think we know yet exactly how common or rare our type of planetary system is. And that's setting aside the question of what do we mean by, you have to define a metric of similarity to the solar system, and it's not obvious what that should be. Other questions?
If not, I have another small questions. Or there is Luca from Android. I guess it's Luca.
Yeah, it's me. It's Luca. Sorry for the Android Blue Droid thing. So it was not as much as a question, maybe more of a comment. I wanted to ask your opinion about the planet population synthesis efforts that are going on some exoplanets theme around the world.
Yeah.
When we say that we cannot find solar systems yet, or things that look like the solar system, I think maybe one of the ways that we can go around the problem is with the work of these people, that they are trying to synthesize entire populations of planets with simulations and knowledge of physics that goes into the planet formation.
Yeah.
But I guess the problem there is more in the planetesimal accretion phase, where people don't know much, as you said. So I guess my question is, do you think that that's a feasible way? Do you think that we will learn more about planetesimals, maybe looking at ALMA disks or any other way?
Yeah, we're certainly going to be learning a lot more in the coming years. ALMA is really, has a lot of momentum now and is delivering the goods. And we're learning about the conditions within these disks and the sizes and masses and the gas content. So that's going to be great, and that will be very helpful. About the, so as a physicist, I really admire the ambition of those theorists who try to model the whole process and produce statistical outcomes that can be compared to this increasingly large data set that we have now. In principle, that's the right approach. And then you fit the model parameters and constrain them by matching the data. I've never done that kind of work myself. It sounds very, very difficult, right? Because the story has all of these different chapters, each of which is going to have some fudge factors or some uncertainties that when you concatenate it all together leads to great difficulty in telling a unique or even any kind of low parameter description of planet formation. Seems very difficult at this stage. And yet our data is such that we can only constrain a few parameters. So I love the ambition, and I think people should be working on that. The immediate progress, I think, comes from more limited comparisons, like the one I described about the radius function, seeing the bimodality there, or the pattern, trying to model the eccentricity distribution of giant planets, or limited attempts to try to gain some understanding from different isolated chapters, with the ambition someday of stitching it all together and drawing a whole flow chart of what might happen within the disk surrounding a star. But you're talking to an observer, so my opinion.
That's why I asked the question. I mean, it's interesting to see how different people, attack the same problem.
More questions? If not, I have another small one.
Sure.
Again, solar systems start to understand what is general, what is chance, like the Titius-Bode law, which tells us about the spacing of planets. Do you know something more now about this law? Is chance or is it a general law?
Yeah, so the Titius-Bode law, for those of you who don't know that piece of jargon, that is a numerical formula with essentially two free parameters that allows you to fit the orbital distances of all the planets except for Neptune. It's one of these things that developed, I don't know, in the 18th century or something, and was regarded as like something that desperately needs explaining, this real regularity that you see in the planet's orbits. Problem was that it never really fit Neptune. It wasn't such a great fit in detail to the other planetary systems. And there have been people who have attempted fitting that same type of parameterized law to the exoplanet systems. It doesn't really work either. So that specific thing, I think there's no significance to it. But the general pattern that I alluded to earlier of kind of a geometric progression and evenly spaced in log orbital distance or log period, that's not an exact formula by any means, but it is a reasonable description of the data. They're not just randomly placed. If you know the orbit of one planet, you can make a prediction better than chance for the location of the next planet out. And I think that that's very important. And what I want to study are these conditional probabilities. If we could map out those conditional probability functions, those should be important inputs into planet formation theory. So I don't think we should expect any kind of cute numerical formula. That's too much. But we can measure the distributions and their conditions, their correlations with one another. That is a very important thing to do. And there are hints of regularities. All right. Well, thanks again, everybody, for donating an hour or so of your time and learning a thing or two about exoplanets. Hope to meet some of you in person someday.
Yeah.
Thank you. And yes.
Thank you very much.
Thanks a lot for such a nice talk.
Thank you very much.
Thank you very, very much. It was very
Thank you, bye.
interesting
Thank
My
you.
pleasure.
Thank you.
and very clear.